Hello everyone, thanks for joining us. Appreciate it's an interesting time, but your time's still a precious commodity and we appreciate you giving it up to come and join us and listen to what we've been up to. Now, Charlie and I work together, we're both data scientists and we both come from an astrophysics background at Leeds University. Physicists find, quantify and exploit patterns in various things, which is good for data science. And astrophysicists are used to wringing the most possible insight from a given telescope before throwing up their hands and saying, we need a bigger boat. So these skills are pretty well suited to a lot of data science problems. There's a lot of creative as well as tech skills. And it's why I went into data science, and Charlie as well. During work, we chat about lots of interesting data problems, everything from healthcare data to this particular thing. And hip hop rhymes came up again and again and again, basically because they've got a fairly mathematical structure to the way that they're built up and the way that the words interact with each other that you don't find, for example, in death metal or folk music, because that's much more about melodies and harmonies and tunes than about lyrical structures. Charlie introduced me to a documentary on YouTube, a Vox documentary that we'll see a few excerpts from, that really does highlight the maths and angle, the maths and structure angle to hip hop, and showed why, for example, words aren't going to be enough to solve this problem. Unlike most data scientists, we were actually put on furlough with COVID-19, so effectively put out to pasture. We took some time to look at this problem and thought, well, you know, let's have a look at it and see if we can use science and our backgrounds to bring some useful insights to the problem, to look at it from a new angle. So this talk is really an explanation of our thoughts and process for the initial stage. It covers the approach to the problem, structuring the problem, and looking at what we can figure out is the base unit of the rhyming currency. You know, what's the barest bones that we can go down to. So for this talk in particular, we've avoided pages and pages of codes. I know some people like it, but we've instead focused on the science and insight part of it. It's using no particularly groundbreaking techniques in data science, sort of standard off the shelf available open source stuff. And the project hasn't been for profit, it's just been for fun and human interest. But it allowed us to choose the techniques, experiment with them, and do what data scientists like to do with it, all without having anybody in senior management saying, very good, but I just want you to change everything, which to me is kind of what it's all about. Charlie's going to jump on and speak about the initial parts, formulating the problem and setting up, and then we'll kind of switch between us for different parts. Yeah, I hope you enjoy it. So pass you over to Charlie now.
Nice one. Thank you very much, Ian. Just wish me luck. I hope this screen sharing thing works. Let me know if you can see the presentation.
Well, I can see it.
Nice one. Just assume everyone else can see it. So we're going to be talking about we first need to understand what rap is and what makes rap sound the way it does. And if we're going to be creating any sort of algorithm to emulate this, the first thing that it would have to do, it would have to make sense. So it would have to produce the right words in the right sequence, and it has to take into account different tenses and grammatical rules. So it would have to pass a GCSE English exam, basically. A level of abstraction above that is it would have to understand what a rhyme is. Is it the spelling or is it pronunciation? It needs to be able to infer different rhyming structures and to follow them on throughout the rap. Finally, probably the most abstract part of this is, on the whole, as a song, it has to have a theme that it follows on smoothly. And as we go around in a circle, we can see we build up levels of abstraction.
Mm-hmm. Well, I think that's the part there that you've got the making sense is policing the sentences to make sure that they're grammatically proper. The rhyming structure is looking at more like a group of lines or 4 bars or whatever, and policing how the words and length and sounds fit together. So you've got the sentence structure, the 4-line structure, and then over on the right hand side, the whole storytelling structure. The whole thing has got to fit together as a document. So that kind of fits with a lot of data science ideas about processing text at different levels of abstraction. So we're going to kind of need to look at all 3.
Yeah, we're going to be focusing more on the rhyming structure. How can we quantify a rhyme and how do we detect them? So I thought we'd warm up with just a clip from the Vox documentary Ian mentioned earlier. So I'll just let that run.
Brakes on car, brakes to make you a superstar. Brakes to win and brakes to lose. But these here brakes to rock your shoes. And these are the brakes. Break it up, break it up, break it up!
So we can see immediately that this is a pretty straightforward rhyming structure, AA, BB. The last words of each line contain very similar spellings. It's also interesting to note that the amount of syllables in these lines mirror each other. So this is a form of a rhyming structure, but it's not necessarily the most complex.
Well, you can see on the top levels, you've got, I mean, each of the lines is adhering to English. You know, you've got breaks on a bus, you know, noun, preposition, verbs in the right places, following the right structures. And then almost like the rhyming part is superimposed onto that by the choice of the end words. But if you look at it, they might have different numbers of words, but actually a similar number of syllables. So we're already starting to see that perhaps we might need to go deeper than words here.
And that lends itself nicely to the next clip, which is from a rap artist known as MF Doom, which is arguably one of the greatest rap artists of all time. So I'll just let that play out now.
Already woke, spit a joke, barely spoke, rarely smoke, stared at folks from properly provoked, mirror broke, hair share, strawberry morning, born more important, spawning, torn in, poor men sworn in.
It's immediately obvious that the rhyme structure of this is far more complicated than the previous clip. We can see that it's not restricted to the final words of each line being the thing that rhymes, but it's actually words within that line. And sometimes it's couplings of words or half of a word that's rhyming with something different. So this is beginning to indicate that the currency of rhyme is maybe something syllabic or phonetic that goes beyond the words or spellings themselves.
Yeah, I think that's clear. You know, the strawberry, it's part of the syllables from strawberry are used in two separate rhymes, with the bare part not really relevant. So we're going to need, if we want to approach this in any way that's going to be able to do anything like this, then we can't just encode these words as vectors, because we will lose that connection between the component parts of the word. So we already know we're going to have to go deeper. So then we look to, okay, well, how deep do we need to go? And this is what brought us. This was the sort of linguistic-y, sciencey part of it, really.
Yeah, so we have to dive into the words and how they're pronounced, essentially, to figure out what the rhyming is inside of them. So just using a couple of lines from that song, just observing that you can see that some of these words are going to rhyme just by the way they're spelled. And we don't need any algorithms. It's really easy to see. I can just highlight some of these now. Woke, joke, and spoke. You know, the vast majority of each of these words is the same, O-K-E. Provoked is an interesting one because the rhyme is actually in the middle of the word. It's not towards the end. So it's easy to spot these. A computer could probably do that analytically, but what's interesting and what will probably trip it up is words like this. So this is spelled a little different, but you and I know it sounds the same, yet that pronunciation is lost in the spelling. It doesn't indicate that they're similarly sounding words. Now, there's been a couple of attempts to kind of quantify rhyming, at least. Now, the first paper, Dope Learning, they've tried to look at the pronunciation of words based upon a dictionary that's hard-coded. They don't use any phonetics or anything. This is quite limiting because the dictionary they use is based upon real official words in the dictionary. So it won't have any names in it, it won't have any slang in it. And we kind of need to be able to pronounce those words if we want to do any rap music. This other paper is focused more on poetry and how it sort of refers to the AABB method, where if you can have contextually similar lines, you just have to have the last word that sounds the same. Now, in this paper, it alludes to the idea of instead of using letters, you use phonemes instead, which is what we're going to hopefully tackle in this paper.
Well, the other good thing from that one as well is that they demonstrate it's a different type of rhyming, but they demonstrated that it is possible to use an LSTM network to generate rhyming prose. So that's almost a bit of a proof of concept. It's given us some confidence that this is a good way to go as well. But yeah, the fact that they mentioned that phonemes, phonetic representations of sounds, could be a better way to proceed than the normal English letters,
yeah.
Which we decided to go with because it avoids a lot of problems, as you'll see.
Yeah. So when you look up a word in a dictionary, you'll see the spelling of it in the definition. Underneath that word, you'll often see another transcription, and it's written in Greek letters, and it's the phonetic spelling of that word. And in the same way that all words are spelt from the 26 letters of the alphabet, the phonetic alphabet, 44 characters, dictates how you pronounce these letters, and it's dependent on where they are in the word as well. So as an example, one of these phonemes is this symbol, which is a U and a weird colon, which says the oo sound. We can think of a bunch of words which have that oo sound in. So we have blew, through, drew, and shoe. They're all spelt completely different, and the part that makes it oo are all different, and they have different lengths as well. So we've lost that similarity. But if we use phonemes instead, we can see that they all retain that similarity because they all have that phoneme within them. So this is a good way of representing how a word sounds, and it's consistent. We can do a similar example. This one is the A sound. So again, bay, made, way, engage. All the parts of those words that make the A sound are vastly different and a little confusing even to an English speaker. Again, if we use phonetics, we can see that they retain this sound. So this is a real good form of currency we can use to kind of pull apart words and find out what it is about them that makes them sound the way they do.
And the other thing that's useful here is that when words are represented by their phonetic representation, the different syllables in the word are explicitly separated by the full stop symbol. So as well as allowing us to match words that you would rhyme when speaking, we can also ignore the number of separate words and concentrate on the number of syllables in a row. Now, some of the other previous work that we didn't mention has looked at encoding hip-hop songs manually so that the right words are on the correct position in the beat structure. Very labor intensive. Now, this potentially, if we look at the top and middle rhyme, the two rhyming matching lines in a hip-hop song, it seems that there's always have a very similar number of syllables in it, regardless of the number of words. So if we're able to break the words of the corpus of rap down into syllables made of phonemes, then we believe that we can also retain some of the timing data information that's implicit in that rap song without having to hard code any musical structures at all, which is potentially a quick win. So that's the other reason that we decided on this format.
Yep, so we've started going down this route because we believe it's the best way to represent pronunciation. But because the English language is so inconsistent and there are so many exceptions to rules that we're going to run into some problems. So here's a couple of lines from the previous song again. It's not immediately obvious this time which words rhyme. Spelling doesn't seem to be as important. If I group some of these words together to show you which ones rhyme, you can see that they're often contractions of words. Now, when you look up a pronunciation in the dictionary, you only find the pronunciation of one word. You can't combine them in the dictionary. You'd have to do it separately. So that's a problem we're going to have to contend with. We also have half of rhymes within words, which is something else that we'd have to hard code into the system. And just interesting to note, the word Tinkerbell is a fictitious name, and names aren't often included in dictionaries, so there is no official pronunciation for that. You and I can figure that out because we know how to pronounce Tinker and Bell, but feeding these words into a neural net.
Yeah, so as soon as you encode a word for data science, you're going to lose that semantic and linguistic knowledge about it. Tinkerbell will just become a number, and there'll be no way, because a tinker is somebody who fixes things and a bell is a thing that rings, and the name's not necessary. So the pronunciation and the meanings and the vector identities would be completely lost. So that's another good reason for us to go down the road we have.
So even before we've created anything that can rhyme, we've got to come up with a solution that will allow us to pronounce any word we give it. So this is where the neural nets come in.
So yeah, what we did is we decided to basically use vector embeddings, but looked at a character level instead of a word. Now, just in case there's any of you out there who aren't so up to date with the vector stuff, I'll just do a super quick review. Give us a click, Charlie. So basically, you take a sentence of words and then you assign those words a number based on their alphabetic position in a dictionary. So they just number like that. this was for a classification task, not relevant here. But then we choose dimensions. So these are degrees of freedom that the words can either match up to or not match up to. Now I've just said between 0 and 1 here. So each word, you can choose a characteristic and decide a number for how well that word matches up to that characteristic. So, you know, queen, female, royal, and valuable are strongly associated. Now, in real terms, this is much more abstract, but this is just a good way to help understand how, using a string of numbers, we're able to basically encapsulate some of the meaning of that word. And this can be an arbitrary number of such dimensions, allowing the learned representations to be really rich. So in fact, give us a click, please, Matt. So yeah, we can remove the words from that and take a guess at what they are just from those dimensions. So a female, royal, valuable, queen, you know, verb implying motion and donating in the past, gave. 3's a bit sketchy, strongly associated with hard, maybe solid. And as you go through, you can see that, you know, we can make a reasonable guess at these words. So we're able to, word vectors are able to basically hold on to all of those important connections that are useful. And our idea is that the same thing is we're going to apply it to characters. Now, it's already been demonstrated that give us a click, Charlie, that the same will work for characters, sentences, paragraphs, and even whole documents. So you can assign degrees of freedom that can allow, say, sentences in how they're related to each other, paragraphs, how they relate to each other. We can lift up the level of abstraction using these same encodings. That to me was one of the big things I've learned in my time as a data scientist, that actually this allows us to treat language far more rigorously than anything in the past. And this is what we decided to go for. But in our case, it's a character level encoding instead of words. So we're dealing with a translation task of translating a sequence of, you know, English Latin characters to a sequence of funny Greek phonetic characters. So, but on a character by character basis. So that's what we're trying to do here. Okay.
So the simplest form of doing this would be a sequence model, whereby you predict a state based upon the previous state. I could run through a pretty simple example. If we just look at this sentence, 1 fish, 2 fish, red fish, blue fish, we can begin to analyze the structure of that sentence based upon things like the amount of times a word is used in a sentence. So the word fish is used more than others, so it's going to pop up a lot more. And using these probabilities, we can start from the beginning and then figure out what is the likelihood that the next word is going to be this, and so on and so on and so forth. So you can build up a sentence just based on the distribution of numbers and their probability. And it can generate sentences that make sense, but it's not going to win any prizes.
Well, that's it, isn't it? I mean, in some of the previous work we've done, we've used models like this, and they produce text that's good enough to fool an algorithm that it's real text and it's unique, but it's not going to win any literary prizes, that's for sure. But it works. Yeah.
So we need a way of kind of improving on this. And the problem with these sorts of models is it doesn't retain much information about things that have happened in the past. And that's where recurrent neural networks come in. So these have the ability of kind of looking a bit further back than just one word and retaining that information to pass on to the next state. So this is an example of one of the states in the neural net. It's got the ability to feed information from the previous state forward and then output something depending on the current state and the previous state. We can unravel this through time, which looks like this, where the inputs are the red dots, and as they go into the system and passed on to the next state, they are combined with whatever came before it. So at the end of it, you have a kind of combination of all the information to make up something in that current state. So I'll give you a better example if we use a sentence. So we split up a sentence into its individual words. What is the first word, and it's encoded, and it's, in this case, it's encoded as a number. Now we can successively add states to this, so the next one will be time, but it's time is a combination of time and the previous state, and the colours indicate how the different proportions change through time. So you can concurrently keep doing this. And you can see that some of the parts that started at the sentence are now they take up less of that circle, and that represents that the network is essentially forgetting stuff that happened further and further back in time. So we're going to need
it's worth saying, obviously, for words that are closely connected in the importance, that's not important, but there are times in English when the key word that changes, say, the sentiments of the statement is quite far removed from the end, and this particular sort of architecture kind of struggles in those situations. So it's known as the vanishing gradient problem in posh terms, but really it's just it just represents the fact that those bands get narrower and narrower, and the more you add in front, the less effect the ones in the past can have.
Yeah. So this is where it's a little bit more technical now.
Yeah, so we came in and this is effectively a schematic of our model. So the number of samples there is just the total count of the number of word phoneme pairs that we were able to obtain. Give us a click, mate. And then basically we map those input characters, A to 0, B to 1, C to 2, etc. It's just a list that maps letters to numbers. Give us a click as well. We basically do the same with the target. So all of the phonetics that you could have become a map into a number as well. So that allows us to translate on the way out. One more, please. Now, the key thing here is what we do is we take the inputs, which could be any number of letters, and we pad those to the longest sequence of the inputs and outputs. So what's the longest input or output? 64 in this problem. Well, let's just make all the sequences 64 long by filling up the ends with zeros. So you can see at the bottom of the white square there, x1, x2, x3 to xn. In this case, n is 64. So every single one of our inputs is now 64 characters long. Give us a click, please. And our encoder input shape is the number of training examples, which is the total minus the validation set, by 64, which is the number of characters for each one. One more, please. And the target shape is exactly the same, except now the targets that we're aiming for are one hot encoded for the standard old reason of ordinality. So there are 46 possible characters in the phoneme set. So we end up with an extra dimension for each of 46 places, and everything's one hot encoded. So there are inputs. We then feed those into the model embedding layer. Give us a click, please, Charlie. Each one's now an integer, and as they're fed in, they get exactly the same treatment as the previous one. Now, give us a click, please. All of the dimensions are 600 dimensions, 600 degrees of freedom in the embedding layer for every single character. Click, and they're initially random values. Now, during the back propagation of the algorithm, while it's tweaking all the weights and biases for the neural net, it also updates these values, so it allows initially random vectors to become aligned in the various ways in which they're connected across the 600 degrees of freedom, and that becomes something that's learned during the training as well. Click, please. And that results in a 3D shape. So now we've got the batch size, which is obviously none in the when we compile it, because there's nothing there yet. And we've got 64 characters, each of which has 600 dimensions. Okay, so from there, the characters are fed into two LSTM layers simultaneously, a forward layer that starts at the beginning and a backward layer that begins at the end. Each of those is treated just like in Charlie's example. We put one in, we process the character, creates a hidden state, passes along, puts in the next one. And inside those A boxes, there are these things called gates, which we're not going to go into here, but they allow the gates to learn which of the inputs are important to remember and forget. And thanks to this ability, the schematic for the LSTM goes from the RNN, which is on the screen there, the same as what Charlie showed you, to the bottom one where the green band and the orange band retain significant importance, even though they're a period of time ago. And that allows the LSTM to remember important features and forget unimportant ones, so it doesn't get bogged down. We also include the backwards direction, because in the case where you've got the whole input, we know the beginning and the end of the word before we try and predict. that it allows the context ahead of the current position to be considered as well as before. And you can all think of cases in English, funny spelling with O-U-G-H and stuff like that, where actually that's quite an important thing. So we slung that in there, and it did lead to an improvement. So have a click, please. Finally, we added a second bidimensional LSTM layer. Abstractly, that allows the network to learn higher level abstractions. In practice, it just works a bit better. And both of the LSTM layers are set with return sequences is true. Now, normally when you've completed the LSTM layer, each of the positions in the A box is giving you an improved prediction, and at the end, it sticks everything together and sends it out. Now, if we set it to true, it keeps the sequences from each stage, and that allows the network to retain the sequential nature of the input instead of just giving one prediction. And that means that we can also use it to predict these sequences with one caveat. So another click, please. So after it's done all that, we send it to a time distributed dense layer. Click, please, mate. So that predicts the output. Now here we've got one node for each phoneme character. So if there's 64 possible inputs and 64 input length, 46 possible output values, we've got 46 nodes, and we hit that layer 64 times to give us a sequence of 64 predictions. And that effectively is our prediction. We can then drop all the empty ones off the end, and the predictions can be all different lengths. But that effectively is, through the experimenting we did, the network that we settled on to attack the problem. It's not the fastest or most efficient, I'm sure, but this is a problem that needs solving once. It's not going to go to production. It's not going to make any money. So it was just about getting it as correct as we could with the facilities and resources that we had. So we did a lot of experimenting, and this is what we settled on. So over to Charlie. Oh, it's a little flashing thing there. Forgot that. Okay, yeah. Oh, so yeah. Sorry, we ran the models using TensorFlow on a GPU. The deep structure permitted fairly rapid convergence, but a lower learning rate to slow that down just often found a local minima instead of the global. So the network was extremely prone to overfitting, and you can see that here, that as the loss and accuracy are sort of converging, the validation loss is going right out of the picture. And one more click, please. So what that top right plot is telling us is that, you know, if we've got a series of points like the left-hand plot and we draw a straight line through, we're underfitting, it's not detailed enough. The middle one's a good fit. That plot of the validation loss tells us that we're moving over to the right-hand side. So we're getting much better predictions in the training set, but as soon as we show it anything new, we're trying to read off that between the points, and you just end up with very, very much less accurate. Now, identifying that was an important thing because it allowed us to go to early stopping and sped up the experimenting. And all we had to do was basically include some code to make sure that we use the best validation loss, revert to that epoch to save the models. So yeah, we found some good results. One more click. Are we going on to? Yeah. So with optimized settings, not this exact run, we got a validation accuracy of somewhere around 97.5%, validation loss of about 0.1. And we visualized the embedding vectors and revealed the characters to be related to each other, but to be also largely independent. So that spinning GIF at the top is a TSNE projection of a 50-dimensional embedding. You can see that some characters are more closely related to other characters, but overall you've kind of got a cloud, which is what you would expect from the base unit of currency of a language. We did some predictive stuff and discovered that you know, this is actually producing outputs that are definitely usable to try and generate rhymes. So in the interests of moving things forward, we were happy with that. I mean, I'm not saying that it couldn't have been done better or we couldn't have found a better result, but it was fit for purpose. Yeah. So we moved on to the next stage.
So at this point, I think I'll show you it working. Now, can you still see my screen, Ian?
Yeah, I can, yeah.
So this is, I've just written a function that takes the prediction, the model, and it First, it takes a word and it encodes it in the way we've described, feeds it through the model, which spits out a prediction, and then we decode it into a phonetic representation. So I'm going to translate these words first. These are names. That's just the word Adele spelled differently. Now, we both know that sounds the same. And we know that these words don't appear in the dictionary, so there is no phonetic representation. If we translate it, oh, I've got to do the whole thing. Just bear with me a second, please. There we go. We can see that it's pronounced both those words the same, and it's found the syllable separation as well. We haven't encoded any names into this, so what it's doing there, it's based upon the English language as a whole. I could do it with my name as well, because there's a million different ways to spell it. So these should all be the same, because they all sound the same, even though they're spelled different. Which they do, which is good. We do the same.
Interesting one there is that actually the T integral sign is how you say a ch in phonetics. So there you go.
Yeah, it's a weird language. We could try it with the word Tinker Bell and Tinkerbell, just to show that it can concatenate these. So it should be the same, which it is. And again, it's preserving the syllable separation.
So it's important to note there that in Tinker and Bell, there's an ER on the Tinker, and there's no R on the Tinkerbell. Well, think about saying Tinkerbell. You don't really enunciate the R. And if this was in a rhyme, it's the at the end sound that is the important phonetic component that would decide whether this rhymed with a similar one 2 lines down. Now, this was part of our study in the predictions. Now, this is where it didn't quite get, this is in the 2.5%, but what we discovered is actually when it matters, when the phonetic sound is important for the rhyme, it gets it right, and it'll just drop an R or something like that, when actually that's reflecting the freedom that perhaps a rapper has in enunciating and pronouncing different words, and even given any accent, they can tweak it a little bit to force a rhyme here and there. So we're not overly worried about this. It remains to be seen. It could come back and bite us on the ass, but
yeah.
I was fairly happy.
Lends itself to the idea that we can bend words to fit other words around, which happens all the time in rap. And I think another important aspect of this is misspelling. Some words and lyrics that we find are just spelt wrong, but we know what they sound like. So if we take the word fractions and fractions spelt with a Z, then they're pronounced the same. So it knows that they sound the same based upon the English language. Now,
yeah, a lot of the lyrics we found online were written by fans, and they'd written it thinking more of pronouncing it than passing an English test, let's say. So there's a lot of words ending in Z. There's a lot of double letters, just one of them dropped. It was quite sort of Wild West in the big data set. So that's a good thing for us, definitely.
It shows how robust it is that we can counter for any kind of mistakes that we might come across. Just for fun, I've tried some rap lyrics. These are words that already exist in the dictionary, so it's not tricky, but it's just to showcase that we can spot rhymes just by the phonetic representation. Palms are sweaty, arms are heavy. We can see that some of the phonemes, they match up pretty well, which would indicate that they rhyme, that full line raps. In fact, we can do the same again with Strawberry Morning, Important Spawning, MF Doom lyrics. So speaking with syllables, you can see that they're the same, which is good. It shows that we can match syllables to syllables, and even the rhyming structure is visible there as well. So
yeah, that's a really nice example, because I mean, you've got the .I at the end of strawberry, but that's almost like, if you think about the way you're saying it, that the Y at the end of strawberry is not a dominant sound in the word, and you can really, with it put like that, you can really see how he's able to bend the rules a bit in order to force a rhyme, and the fact that it facilitates that is, I don't know, it makes me feel a little bit more confident that we've chosen a useful route to go down. So yeah,
we can just spot from the phonemes that it sounds the same and even has the right syllable structure. So I think that's a win. So we've got a translator that can turn any word we give it quite accurately into a phonetic representation. So we've combined that with a corpus of rap that we've obtained, which is about 50,000 songs, I think.
50,000, yeah, odd. I mean, some of them weren't hip hop, and some of them were duplicates, and some of them were the clean version. But I think after we ripped them down, it was about 50k. And we ran them through. It took, I don't know, it took a while, but we've done the translation. So we have got those songs broken down by lines and verses and all the rest of it, as per what Charlie just showed. Yeah,
we've successfully transcribed the rap into a corpus of syllables and phonetics, which is more useful to us. The spelling doesn't really tell us much about the pronunciation or the timing of the words, but a corpus of pronunciation is going to give us way more information. The corpus of phonetics, if you think about a corpus of words, using word embeddings in vectorization, we can map semantic connections from word to word. As Ian described, we can find that king and queen are really closely related. We can do a similar thing with phonetics, where we'll be able to group phonemes and similarly sounding words. It's a very similar process. And this is basically just learned rhyming patterns. Now, once we have learned rhyming patterns, which we'll use another LSTM to do that, and we can have semantic vectors from other word embeddings, we've got the ability to understand rhyme and rap, and we've got the ability to tell a story. If we combine those two things, that's rap, and that's going to be the next stage after this. But yeah, I think we succeeded in doing that.
Yeah, I think it's the other key thing that we'd like to do is, now that we've got the phonemes split down to syllables by the word boundaries and the syllable full stops in the words, what I'd really like to do is to try and encode syllables as vectors. So I think I pulled apart the corpus. There's something like 25 to 30,000 unique syllables across the corpus. And it seems to me that actually, if we treat each of those syllables as a unique vector, then we're going to start getting some really interesting connections between how those syllables correspond to each other. And it's far more abstracted than the word vectors, because it is specifically a syllable is a unit of pronunciation. So it's almost like where the word vector embeddings were looking at, semantics that makes sense. This is just going to be saying, well, in what ways do these sounds relate to each other? How can this follow this, or this, this sounds the same as that? And I'm really hopeful that actually, if we can get a good vector representation of syllables, that we will be able to make some good progress on this. And this is where our approach diverges from the other approaches that are just kind of throwing brute force at it. And instead of that, we're thinking, well, let's look at it with a little bit more subtlety and try and get down to the basics. But it justifies the efforts that going towards making this phoneme translator, because if you feed a network crap, you get crap out. So we've really got to make sure that we get this bit good, or decent at least, and then hopefully the next part will take care of itself. But yeah.
We suppose approach it in the sense that when you're trying to rhyme something, you have to make the words fit, and then you have to make the words fit rhythmically. And that's the approach we're taking. We're going to try and make the words sound the same, whilst also carry on a semantic continuity. So it's the same principle, but at this point, we've succeeded in the first step.
Yeah, and I think that it's actually, boom. I think it's actually a pretty important step, and I'm pretty happy that we've found a new way to look at the problem as well. So it's yeah, I mean, just to sort of sum up as well, we're just two guys in Leeds on furlough having a bit of fun with it. I'm going to get the whole thing up on GitHub in the near future. If anybody out there's got any insights, any interest in this kind of stuff, feel free to get in touch with us through the guys at the festival, or through through our connections that are listed on our bios, or however you like. It'd be great to hear from. I mean, all my friends are suddenly interested. All my friends who like hip hop are suddenly interested. They just don't have the data skills. But anybody who wants to get involved, jump on. Thank you. Enjoy the rest of the furlough. Look after yourselves. Cheers.
Well, cheers.
Did he say now we're supposed to tell Dave to come back in? Is that what it is?
I'm a professional.
Well, Dave, thanks.
I'm back. Man, that was fantastic, guys. Absolutely love it. It was really interesting talk, very thought-provoking. And as I say, I think I've probably got a little vested interest. Well, personally, I love that type of music, so it's all good. We've actually had a comment in the chat already come through, one of the best Zooms that they've been to so far, which is
thank you.
Nice.
Very kind.
Nice one, thank you.
Got a couple of questions. You know, by all means, guys, if you sat there still watching and you're thinking of anything, you know, don't be shy, stick it in the chat, and we'll go from there. The first question actually coming from Matthew Sharp, and he was talking actually how much experience in applying NLP techniques did you both have, you know, before embarking on this fascinating project? Did you both use NLP in your day-to-day jobs?
Well, basically, where we work at the moment, I've been there longer. I brought Charlie on board. I've been doing NLP in classification tasks as a project for about 2 years. The task was completely different though, and it was basically a classification task using word vector embeddings, Markov chains to simulate stuff to fill in missing data, and then a deep learning classifier to basically match text to particular, what's this advert for, what product's it for, that kind of thing. But I hadn't done any sequence generation. I'd looked at, I mean, everybody's watched Andrew Ng's videos and all the rest of it, so I was familiar with it, but we thought we'd use the furlough as an opportunity really to just plow into it, because the best way to learn anything is to just, you know, watch Andrew Ng first and then have a go at it afterwards. So that was the thing. So I've got a couple of years experience, but not in sequence modeling. This has been our first effort, mine anyway.
Yeah, I've had some experience with working with Markov chains before. I actually used one to make a really rudimentary rap bot some time ago, where you just basically pick the next word depending on what words came before it, and then you just say, right, make them sound the same. NLP,
that's where this whole thing came from, isn't it? I've forgotten about that completely,
But as far as NLP, it's more just what I've been doing in my own time for this project, and it's just an entire field, so there's still so much to learn about. But it's massively helped this project. It essentially uses all aspects of NLP science to push this thing forward. So
well, it's just, I think that the rap as well, you know, everything aside, that the rap's got all the elements of NLP in it, right? I mean, it's got the most, from the most sort of simple aspects of sentence structure from the old school, you know, verb, preposition, point of speech, tagging and all the rest of it, right through to the most abstract, like how do we tell a story that hangs together through multiple sort of paragraphs, as it were, throughout the whole document. As he said on the first slide, it's really trying to match from the top to the bottom all of these techniques. And well, how far we'll get with it, I don't know at this stage, but it's just, I don't know, it like with everything, it's a chance to use the tools and get your hands dirty and see where you go with them. That you never, it's never a waste of time getting good with these things, I don't think. So getting better experience with
it's been fun just trying to understand it all, really, because some of it's quite abstract. And I think that's where the most interesting sciences are. You can't really comprehend what it's doing. So yeah, it's been fun.
Yeah,
I think building up that corpus, building your playlist, it'd be a hell of a Spotify playlist, lads. I think you should share that. Never mind.
Well, it's I mean, well, this is the thing, because a lot of the sequence stuff, like what we were looking at with the phonemes, it hasn't been done with text to text. But if you look at the speech to text, so like trying to take spoken words and encode them, obviously you're dealing with an audio signal translating to text, so you have to go through the phoneme. So that side of it isn't completely groundbreaking, but nobody's applied it to text data. And some people said to me, well, look, why don't you just get all of the hip hop albums and just get the text out of them that way? And I'm like, yeah, that's a whole other can of worms. Do you know, like I've got enough fish to fry here already, thanks very much. So we decided to, cross the two and let's take this element from speech to text, and then let's take the old text to text translation and just mash them together and see what we come up with. And yeah, like I said, this is the great thing about data science, right? We're two guys. We haven't got access to any insane resources or anything like that. And we can do it just as a bit of fun, you know, just in our spare time or furlough time. So I think that's another great thing about doing data science, is that it's open to everyone.
Agreed. We've got a few more questions coming in, actually. So we'll fire through them. Christopher Reeves actually saying, go on then, show us an example of the output. Are you guys at that point now where you can produce some output, or is that,
Well, basically what we've got now is, as we sort of said at the start, like you've got the rhyming structures and patterns. So what we're at now is basically we've got a corpus of 50,000 rap songs that are encoded in this way. So the very next stage is to basically, and this is an open question, perhaps somebody's got some good ideas on this. I've been running through it a little bit. What do we do with it? Like, what's the best way to go? There's an example out there of typing a few keywords into a page and it spits a verse that's related to those keywords. Do we take a line, generate a line, and have the algorithm generate the rest of 4 bars? I mean, it's all possible. Now the initial idea that we had for this thing was, let's try and create an AI that can do AlphaGo, because it's going to make a way better documentary, right? AlphaGo was great. I didn't even know what Go was. I was fascinated by the human interest story. Now, take AlphaGo and add the machoism and showing offness of hip hop culture. And that, I don't know, I just like imagining like a system that can take an incoming stream of either audio or text encoded, and in close to real time can spit something back that is, obeys the rules of English, rhymes, and slates the guy or girl who put the original thing forward, which is the whole rap battle thing. And for me, that would be the ultimate goal in the end, to get it to be able to do that. But the first instance will be to have it create rhymes from not rhymes, I think. So we're not at the stage yet. Unfortunately, we've both had like other projects and stuff that have come up. But what we've got, this is like our touting to reel some people in. We got this data set, right? I'm not going to, we'll get it on GitHub and what have you. So if anybody out there has got ideas about what to do with this and how to make it useful, let's get on board with it. But yeah, I did want to make it clear. Yeah, it's not a rhyming. It's a journey into the belly of the beast, because unfortunately we thought we'd be able to just stick a load of stuff in and get a rhyming algorithm. And then pretty quickly it was like, well, it's going to be a bit more complicated than that. So yeah, to hold our hands up. It's not spitting verses yet, but give it a bit of time and or the right people to get involved. And it could be a quick turnaround, I think. So yeah.
That's a question from Adrian Bayliss saying, really interesting stuff. What's the best way to keep updated? So I think we'll follow up with the attendees after this. We'll share the links, connect everyone up, so you guys can all see.
Like I said, I haven't done it yet, but I'll just get this whole ML Doom thing on a GitHub, and then anybody can have a look at the code we've done, look at the data set that we've got. We'll get everything up there, and then anybody who's wants to have a look at it, give us stick for not doing it the best way, or suggest anything better, then, or just get involved would be great as well. So I mean, we'll put all of that stuff through to you guys as well, and make sure that you can get the word out as well.
Perfect. Next question was from Alexei Simonov. Do you think training Generation Net on general poetry, presumably a much bigger corpus, and then fine tuning for rap would help, or I mean, I'm assuming you guys thought this anyway.
Yeah, the reason for that was because it's already been looked at a little bit, and because it is a big corpus and what have you. We thought that sometimes you find that less is more, that perhaps we can get at least a good insight out of stripping this stuff into syllables built of phonemes. And then, as my rule is as a data scientist, is, don't use a sledgehammer to crack a walnut. If we can fix it with what we've got, let's do it with that. The other side being that poetry, I don't want to say it's not as constrained as hip hop, but it doesn't have a lot of, not all poetry, but some poetry is a little bit sort of free-formy as well. And what I would want to avoid is an algorithm training on stuff that is not as rigidly structured as it needs to be to do hip hop. So I would say, let's try and do it with the rap songs. And if we need more, then we would go to the poetry after that. But it is a good question. And that paper that's in the thing is an interesting read as well. It was a master's project, I think, but but they had a good go at it.
Rap, the point of rap is it has flow and a beat, and it has rhyme structures that will change throughout the song, but it always has those things. whereas poetry is more just, it doesn't necessarily have to have any of those things. So as a training set, it wouldn't be as consistent.
Yeah. I think that necessarily, because some poetry is very much like rap, but some isn't as well.
Yeah.
And I'm always for the clean training sets, definitely.
Yeah, but poetry is just not as good as rap, basically.
Well,
you said
glad
that.
you said that, Dave. You can hold the controversial mantle if you like.
Next question come through from Mark Barrett. He's quoting Biggie, so he gets like extra points for this one. I think we've kind of answered it already, Mark, but he's looking to see where you're going in terms of rap.
It's not Who Shot Biggie, is it?
No.
Oh, good, because that's a can of worms, man. I think we might be getting trapped or something. I can't talk about that, Mark.
Yeah.
But yeah, down the line, we'll all be there for the first rap battle. It'll be like, Deep Blue versus Gary Kasparov, but we do against Eminem or something like that. It's
Yeah. Exactly. That's what we're aiming for. That's what I would love to do. I just think the idea of having that server rack on the stage with a smoke machine behind it and a glitter ball above it would just be. I mean, you could have so much fun with it, with the giving it an avatar, giving it a voice. I was looking at that Avartify, is it, or something where you just get Einstein to speak, and I was like, oh, we could have so much fun with this. I mean, the way you go with it could be anywhere.
Watch this space, Mark. Watch this space, basically. Next question from Hamad. Again, we've kind of covered that one off. What a super inspiring project. How can I be useful further? Again, we'll connect everyone up and follow that one up. Thordis, do you have any examples, or my screen's moving about all over the place. Do you have any examples of outputs you've generated? Great talk, by the way, really enjoyed it.
Well, this is the thing, the outputs that we've generated at the moment are the translations of the existing rap songs. So we've got 50,000 existing rap songs by everybody from, Grandmaster Flash through Biggie to MF Doom and even all the new stuff. We've now got that encoded in a way that we can use it in a machine learning, deep learning environment. We haven't done it yet because we haven't had the time, and we've both been involved in other projects. And part of it is just we're trying to figure out what to do with it. There's a bunch of different ways we can go at it. Who knows? That's why it'd be great to have extra people, because somebody can pick it up and do this with it. Somebody can pick it up and we can just see which works. But no, we haven't. But what Charlie did do is demonstrate that actually with these phonetics, you can spit out words that rhyme effectively. So the rhyming part, from just what he said, we know it works. From the way that embeddings work and the way that I know from words, I know that the syllable embedding will embed rhyming information if we give it enough dimensions. So how well it will work is open, but it should work at some degree, just given the logic of the vectors and the way in which all the other processes work. It's just, but the application of it, how we do it, that's completely open. But do we feed it a line, get it to spit a bar? Do we feed it, a couple of keywords, have it spit a verse? I don't know. And answers on a postcard to data idols.
Yeah, thanks, mate.
Boredom.
Next question from Adam. Really interesting talk. Thanks a lot, guys. As I understand it, your current method is looking at syllables in a bar. I'm curious as to your thoughts on how additional input could be added that looks precisely at what beat of the bar each word falls on.
Some of the phonetics, they actually encode the enunciations or the what parts of the word you stress. Now, a lot of that does fall on a beat. It's where you end the word or the middle of the word. So I think some of that could be encoded in with the phonemes, if I'm not mistaken.
And the syllable gaps as well. I think we did. There's a data set out there that some people spent a long time on that actually has lyrics with the, if you imagine the bars like as lines, actually having the words across them, so they're representing the right amount of space to take up. What we're hoping is that by representing these syllables with the gaps, you'll have gaps between words, you'll have dots between syllables, that looking at the rhymes, that looking at the verses we've put through, actually the lines that are rhyming with each other tend to have same plus or minus one or two syllables, and then maybe the other rhyming lines have got a different number of syllables. But that consistency between the rhyming lines is an abstraction of the underlying beat. Now, it doesn't give you all of the information about it, but perhaps we don't need all of the information about it to just know you need a syllable here that ends in that sound, and a syllable here that ends in that sound with that many syllables in the middle. That it might work. Again, we're not sure yet, but in the interest of doing the least work for the most output, I will come to that bridge when it proves to be absolutely unavoidable. Because if we wanted to encode everything to beats, that would be a lot of work, or you know, an entire other project in and of itself. So if anybody's interested, you know, jump on.
Come on. Carlos has asked the question: how long did it take to train the model after the data had been translated to phonemes?
Well, it took at the full resolution one, it was because we were running it on GPU. It was about 3 minutes per epoch. Now it converges after 10, so 10, 15, so maybe like less than an hour per run. But then obviously we are running it a bunch of times and finding the best settings. I'd say the whole experiment in finding the best one, producing the model, was about 2 weeks, give or take. Of you know, once we've got the dictionary of words to phonemes, maybe 2 weeks. But yeah, it's about 30 minutes per run on one GPU.
Sweet, fantastic. We've got one more question, which takes us exactly to 2 o'clock, which is absolutely perfect for our lunch hour session. Umberto's working on this project and he'd like a bit of input, I think, so you can help him out. How would you go about extracting the most important parts of a text? So say you want to summarize a text. In that case, it's not pronunciation that matters, but meaning. Well,
I would download one of the pre-trained word embedding sets like Glovo or something from Word2Vec, and then you've got all the semantics. And then I would basically encode all of my text to that, and then you don't even need to run anything on them. I just look at an analysis of the word vectors in the sentences, and from that you can probably, I mean, it depends on when you say the theme, it's I don't know, it's are you classifying science abstracts, or are you looking for hate speech in tweets? It depends what theme you're trying to identify as to what you would look for. But those word vector embeddings potentially have got every information that you could want and more. So I would go that way, I think.
Perfect. Awesome. Right, that's brought us to a close, bang on 2 o'clock. Just kind of leaves me to say thank you very much to you two guys, Charlie and Ian. Absolutely awesome.
Thank
you.
You guys that are watching, you know, if you've enjoyed it with the guys, please follow up with the guys. You know, say thanks to them, you know, online or wherever. Drop them a little message, because they've given up their time to share with the community.
I've also been sat in my house for 9 weeks with just a 7-year-old for company. So, you know, any grown-up chat is always appreciated.
Ian wants some interaction, so send it especially. So, but that was absolutely awesome, guys. Thank you so much, and we'll have you guys back. No doubt about that.
Thanks for having us, mate.
Yeah, thank you very much.
See you all soon. Bye-bye.
Bye.
Yeah.